Okay, AP Environmental Science students, this is topic 1.4, which is the carbon cycle. So we're going to continue with our lectures here about the different biogeochemical cycles. So we'd already talked about the water cycle, which I think was kind of an easy one to understand if you just kind of understand the terminology. The carbon cycle, I don't think the terminology is that difficult. It's just there's a lot of different things going on in the carbon cycle. So when we get to the diagram today, it looks a little bit daunting at first, but it's really not too difficult if you kind of pay attention. All right, so first, little bit about carbon, why we should understand it. The carbon cycle is, pretty much, or carbon is an atom that is found in all living things. It's kind of the backbone of life. Organic compounds, things like proteins and DNA and all these things that you talked about in biology class. They're all carbon based. So, kind of understanding, how carbon cycles itself around our planet is a pretty important thing. Most of the carbon that's on our planet exists in compound form. It's either in the form of like a gas, like carbon dioxide, or something like methane gas, which is CH4, which is basically natural gas. It might be in the form of solids like calcium carbonate, which is limestone. But again, there's an abundance of carbon on the planet. We just have to kind of understand how it's kind of moving around and why it's important that we kind of know this. Okay. Processes in the carbon cycle. So again, just like the water cycle and all these other cycles that we're going to kind of learn about, carbon moves from like the biotic to the abiotic factors, in every cycle or in every ecosystem. So again, carbon is found in every living thing. It's found in the atmosphere. There's carbon dioxide in the air. It's a greenhouse gas. Methane, the same thing. It's a greenhouse gas. It's found in our atmosphere. It's found in permafrost in the tundra. We talked about that with in our biome um, unit or biome topic. That there's so much of that permafrost melting that all of that methane gas is going up into the air and it's increasing global warming and causing our planet to heat up even more. So that's not a good thing. A lot of carbon is found in the ocean, and you'll see that in a minute when we talk about the cycle. It's found in fossil fuels. We'll talk a lot about fossil fuels this year, things like coal and oil, for example. Photosynthesis and cellular respiration are a major part of this cycle. So you'll hear me referring to those two processes a lot when I explain the cycle, but they're kind of opposites of each other, right? Plants photosynthesize, animals um, and other heterotrophic organisms respirate. So that's called cellular respiration. All right, now before I get into the diagram in a second here, here's a term I want you to understand. It's called a sink or a carbon sink. Sinks are just areas on our planet where there's a lot of carbon that's being stored. Now, you'll hear me refer to sinks when I talk about phosphorus and nitrogen as well. But on the planet right now, the biggest carbon sink that we have is the ocean. There is a ton of carbon in the ocean. Forests are another one. There's a lot of carbon on land. In the forest, there's carbon in the soil. There's carbon underground in like fossil fuel deposits. There's carbon in the atmosphere. So these are all different sinks, but far and away, the ocean is the biggest carbon sink that we have. Okay, so here's the diagram. This is my diagram that I made. I'm actually kind of proud of this little diagram, but anyway. The one that you'll see the lady talk about in the AP Daily video, I think that video's got a little bit more going on than this one does, which doesn't make it any better. I think trying to keep it as simple as we can is, I think, the easiest way to learn it. So I think this is kind of a simplistic video. but or a simplistic drawing or diagram. We just have to kind of understand what's going on in each kind of step. So what I'm going to do here, I'm going to start over on the left-hand side here. Okay, we'll kind of split this diagram, up between like the ocean, like the aquatic side versus like the terrestrial side. All right, so I'm going to talk about the aquatic side first. So again, I just mentioned this that the ocean is like the biggest reservoir or sink on our planet of carbon. There's a ton of carbon dioxide in the ocean. Now, how does all that carbon dioxide get there? All right, if you kind of look at these two arrows, there's an arrow here that's kind of pointing down to the ocean. There's another arrow here that's kind of pointing down to the ocean. All the carbon dioxide that's in our air, all of that stuff can make its way into the ocean through basically two processes. One of them is photosynthesis, so all the aquatic organisms that live in the ocean, and there's a lot of them, especially algae, they absorb carbon dioxide from the atmosphere, and that brings it into the ocean. Another way that carbon gets into the ocean is just through the process of dissolving. It just diffuses right into the water. Okay, so both of those processes kind of bring carbon dioxide into the ocean, and then it can be used. Now, there's also organisms in the ocean that are going to produce carbon dioxide. Obviously, we have fish and any other animals that live in the ocean. They're going to give off CO2. So that's why this arrow here is kind of pointing up to the atmosphere from the fish because they are producing that CO2. And you'll also notice that there's a little arrow pointing away. Some of that carbon dioxide that the fish produce, that stuff stays in the ocean and it can be used by algae and plants and things like that. So we've just got this nice little balancing act going on between the carbon dioxide coming out of the air, being pulled in by photosynthesis. And then you have cellular respiration by the fish and the animals that live in the ocean, and they're producing it. It's going back up into the atmosphere. Now, a little bit more, of what's happening in the ocean. Down here at the bottom of the ocean, we have decomposers, right? These are organisms that will eat anything that dies, including all the plants and all the fish, all the animals. So when those things die, well, first of all, those organisms, they also produce CO2. So whatever they're doing down here, eating all the dead plants and animals, they're going to be producing more CO2. So that's again going to go up in the atmosphere. So you'll notice this line here. It kind of follows along the cellular respiration line. It just goes right back into the atmosphere. Now, a couple interesting things happen when it comes to the decomposition. There's two like major things that occur. One of them, this line here, you'll notice where it says time. And whenever you see this, that means like this is a long process. A lot of living things that die, when they get decomposed, all that organic matter can get turned into fossil fuels. For example, oil and natural gas are fossil fuels that are produced by decomposers that live in the ocean. But again, this takes a tremendous amount of time. We're talking millions of years for these oil and natural gas deposits to form under the ground through this process called burial. But all that is just the decomposition of dead matter, and it's just producing a fossil fuel. But again, it takes time. The other thing that could happen is a process called sedimentation. This is a process where carbon-based compounds, from decaying matter, can be turned into calcium compounds. The most notorious one is calcium carbonate, also known as limestone. This stuff will start building up and building up and building up in the ocean, and it's been doing that again for millions and millions of years. So again, you'll notice time. This takes a long time. But I mean, all of this limestone that's in the ocean, there's carbon in it, as well as all the other carbon, all the CO2 that's in the ocean. This is what makes the ocean such a big sink. It has all that gaseous carbon in the form of CO2, and it has all that solid carbon in the form of calcium carbonate. Okay, now let's move over to land. So again, on land, we see a lot of things going on up here on the surface. But starting off over here, we see kind of some of the similar things that were happening in the ocean, right? We've got photosynthesis happening with plants. So they're drawing the CO2 out. We've got cellular respiration by animals and also by decomposers that live in the soil. So, these decomposers, again, they're eating all the dead plants and animals and everything like that. So they're doing some very similar things that these decomposers were doing in the ocean. But these guys are strictly just producing fossil fuels. When they decompose organic material, if it gets buried over time, again, time, over millions of years, all that decomposed matter could end up turning into fossil fuels such as coal or, again, natural gas. All right, but again, that takes an extremely long amount of time, and those things can build up underground. Now, of course, all of those fossil fuels, coal and natural gas, can get extracted, and they can get extracted quickly. For example, here's an oil derrick. Once an oil derrick, drills into the ground, once they tap into that oil, for example, they can bring that up in a matter of days. So, I mean, think about something like oil that took millions of years to form. We can now extract it in a matter of days, process it, and we can burn it. And when you burn it, it produces CO2. So that stuff can go back up into the atmosphere where it hasn't been in millions of years. But again, this is an anthropogenic thing. We're kind of pulling all that out, we're burning it quickly, and we're increasing the amount of CO2 in our atmosphere. Same thing with automobile emissions. Okay, that you know, gasoline is a product of oil, and again, by burning that, it can increase our CO2 content. Another thing too is you see this little guy on the tractor here. Soil disruption. There's a lot of carbon in the soil. When you disrupt the soil by any means, agriculture is a big one. When that soil gets disrupted, a lot of that carbon can go back into the atmosphere, just through the tilling of the soil and things like that. So again, these are all anthropogenic things that can put that carbon back up there. Forest fires. Now, forest fires could be natural. They could be man-made. So I'm not going to say all natural or all fires are the result of anthropogenic activity. But again, when trees burn, there's a lot of CO2 that's going to go up into the atmosphere. Right now, every year around this time, you hear about these wildfires out in California that are burning like crazy. Think about all the CO2 that's going up into the atmosphere. Okay, so that kind of does it for the diagram. I think I did a pretty good job explaining that. I hope so. You can always kind of go back and rewatch it again if it didn't make sense to you the first time around. One more thing, real quick here. The human impact on the carbon cycle. I already mentioned these a little bit, at least the first one. But there's really two major anthropogenic activities that really kind of knock the carbon cycle out of balance. One of them is fossil fuel use. Again, fossil fuels extraction and then burning it, that really decreases the sink that's underground, and it increases that atmospheric CO2, and that's linked to global warming. Again, CO2 is a greenhouse gas. Another one is deforestation. Trees again will absorb CO2. So when you cut them down, that's going to cause CO2 to be released, not only from the tree itself, if it gets burned, for example, but also from the soil. A lot of times deforestation involves a lot of soil movement, and that will also help to release CO2 into the air. So these are two really bad things for the atmosphere and for the disruption of the carbon cycle. All right, guys, that's it for me. Last slide here again just kind of shows you the essential knowledge. Make sure you read this. I think I covered most of these things in my lecture today. Also, I would watch the AP Daily video on this topic. It's a little bit, I think, a little bit more difficult to understand than my lecture, but give it a watch anyway. It can't really hurt. All right, guys, have a good day. I'll see you soon.